Okay. Can you all hear me okay? Not really. Do I need to move this closer?
Okay, welcome. Thank you all for coming. I just want to remind you that next week we have David Allen, who's a professor here at the university in the chemical engineering program. And today we have a very special event where we've invited a current and former students to present on their research. Our first presenter, Charlie, has been a PhD student here as well as an undergrad. He's going to be talking about modeling peak load reduction and energy consumption enabled by integrated thermal energy and water storage system for residential air conditioning systems in Austin. And Charlie is going to be, after Charlie we're going to have Erik Funkhouser, who is a former student of the LBJ School of Public Policy, and he is now working at the Energy Systems Transformation Group at the LBJ School. Erik has done research across the policy spectrum, and his current research includes international low-carbon technology transfer in the U.S. solar market development and early-stage investment in clean tech. Erik is also a fellow at the Breakthrough Institute and advises outreach and partnerships for connecting Congo. So we're going to start with Charlie Upshaw, and I'll let you know when your 5 minutes are closing in.
All right, sounds good. Thank you. Can you all hear me okay? All right, great. So my name is Charlie Upshaw. I'm a PhD candidate here at UT in the Mechanical Engineering School. And I'll be talking about modeling peak load reduction, energy consumption, enabled by an integrated thermal energy and water storage and management systems for residential houses. That's kind of a mouthful. I'll get into what that all means. So quick overview, I'll give you a motivation introduction for these integrated systems, discuss the system design and operation, thermal modeling and analysis of why these might be potentially useful, and then discuss some conclusions and future work. So motivating issues, two primary issues, long-term water and energy constraints here in Texas. So from the water side of things, the Texas Water Development Board is projecting severely constrained water resources into the future, 22% increase in demand by 2060 coupled with a 10% decrease in supply by 2060 means that there's going to be more water demand and less to go around. And one of the big drivers of that is municipal consumption. The population is projected to grow by about 80% in that time frame. From the electricity side of things, ERCOT, which is the manager of the Texas electricity grid, they're concerned about generation capacity and grid reliability stemming from peak demand, which I'll discuss what that is in a second. The growing demand is being fueled by this growth. This 80% increase in population demand, they're going to want water and they're going to want electricity. And so that's one of the kind of growing issues or long-term potential issues. There's also an increased potential for extreme weather. I think something like 9 out of the 10 hottest years have been in the last 20 years, something like that. Our climate's warming up, whether or not you would like to admit it or whether or not you blame people. It is contributing to the grid stress. And then there's also not enough new generation being built. This is for a combination of reasons. Low gas prices, low electricity prices, not really incentivizing new construction for new capacity. So what can be done about these two issues? One thing that could be done is auxiliary water systems, auxiliary water being rainwater, gray water, and AC condensate or air conditioner condensate, could help reduce residential water demands. So rainwater harvesting, it's viable for almost the entire state from a precipitation, the amount of rainfall that falls from that perspective. It can be used for potable water if it's treated to a certain standard. It can also be used for irrigation. The problem is that you need significant volume to be able to capture enough water to significantly reduce your water consumption, your municipal water consumption. Gray water reuse, that's water from bathroom sinks, showers, and laundry. It can only be used for irrigation in Texas in residential homes. You can't bring it inside the home for reuse in any sort of way. And then AC condensate is a small but steady source of water when rain is typically scarce. The problem with auxiliary water systems is that they need to be large enough in capacity to be effective. I'm talking primarily about rainwater here, gray water as well. They're typically not economically viable because of the size that you need to compete on a price perspective with municipally treated water. So that's for the water side of things. That's one potential solution, but it has some drawbacks and some roadblocks. From an electricity perspective, peak load, which is the amount of electricity required from the grid at any given time, it's driven by air conditioning in Texas. This figure shows the change in peak load. This is in the kind of 515 in March of 2011 versus August of 2011. The load on the grid more than doubles, and the reason for that is air conditioning, and it's primarily residential air conditioning. If you say, okay, in March 2011, March 9th, there aren't any air conditioning systems on. It's 70 degrees outside and nice and pleasant. In August, I think it was 104 that day. All the air conditioning systems in those houses are on. That's 26 gigawatts, or about 38% of the peak load. So it's a huge contributor to the peak load in Texas. Unless capacity increases to meet this peak load, as more and more people move here and build more houses, users could face higher prices or they could face lower reliability. Thermal storage is a way to shift air conditioning load off peak. And the way it works is you pre-cool the thermal storage mass using your air conditioning system, and then use your thermal storage instead of your air conditioner on peak to reduce the demand. So this reduces or eliminates entirely the compressor load during peak hours. The compressor is the thing that draws the most electricity. It's the biggest consumer of electricity in the air conditioning system. This picture shows UT's thermal storage system. That's the chiller plant. It has power drawn the order of tens of megawatts. This is their thermal storage tank. When their thermal storage system is operating, it's on the order of several hundred kilowatts. So it's about an 80% reduction in power. The problem with thermal storage is that it's prohibitively expensive on a small scale. It doesn't scale down very well. The cost per kilowatt hour shifted is not as much traditionally to be viable at the residential level. So the idea that I had was maybe if you integrate thermal energy and auxiliary water storage systems into one system, maybe they're kind of, by combining them, you could maybe reduce some redundancies, get the benefits of both without having to pay for entirely separate equipment for both. I call it iThirst DX because it's kind of catchy and it's the best acronym I could come up with. That stands for Integrated Thermal Energy and Rainwater Storage for Direct Expansion Air Conditioning System. So I'll refer to it as iThirst just because it's hard to say integrated thermal energy and rainwater storage repeatedly a lot. I have said it a lot, though. The idea is to use the rainwater, use the thermal mass of the rainwater in the thermal storage system. And the goal is to reduce both peak electricity demand from residential houses and municipal water consumption as well. And my hypothesis is that an integrated system will provide better net value than two non-integrated systems by reducing individual system redundancies, primarily the storage tank, and also making use of an otherwise unutilized thermal resource. So the design scenario for my analysis focused on housing in Austin because I'm from Austin, and like every Austinite, I think this is the center of the universe. So I designed it around a typical Austin home. This is based on energy audits from Austin. So Austin requires you to get an energy audit if you sell a house. We got all that data. It was like 12,000 houses, did some averaging on it, and used that to pull out the kind of parameters for modeling the house in an energy simulation software. 1,800 square foot approximately, using a traditional direct expansion air conditioning system, roughly 3 tons. If you know what that means. If you don't need to worry about it. It's not important. And the only difference for this kind of assumption is that you have a large auxiliary water system that you're using for irrigation that you're now going to be using for thermal storage. So system design and operation. This figure is schematically how the system is laid out. It's not this cartoony in real life. This is a traditional air conditioning system right here. It consists of an outdoor condenser. That's the big thing with the fan outside. Compressor, it's usually inside the box with the condenser. and then the house evaporator inside. The way this works is the compressor compresses refrigerant up to a high pressure, and it's at a high enough pressure and temperature that the outdoor air can condense it back down into a liquid. It's then expanded through this expansion valve to a lower pressure, and part of the thermodynamics of the refrigerant are when it is expanded it to a lower pressure, it also goes to a lower temperature. So that's how you get a nice low temperature in your evaporator. You then boil this saturated mixture at about 40 degrees Fahrenheit or so, and then all that vapor then goes through, and that's kind of the traditional air-cooled direct expansion system. The system operates in that mode during kind of the early morning, or the morning hours and early afternoon before the peak time period of 3 or 4 to 7 p.m. Sorry, wrong keyboard. In thermal storage discharge mode, what happens is the compressed vapor bypasses the air-cooled condenser and goes through a heat exchanger that's being cooled by water from the tank. The condensed refrigerant then goes through the same expansion valve into the same evaporator for the house. This is at a much lower temperature than the outdoor air, and I'll explain why that's significant on the next slide. For recharge mode, instead of going to the house evaporator, what happens is it goes through and into this heat exchanger again and cools the water down just like you'd be cooling the air down inside your house. So from a thermodynamic perspective, the benefit of using this water as opposed to the outside air is it is a lower temperature and therefore a lower pressure. This is a pressure enthalpy or pH diagram, and it's used by mechanical engineers and others for laying out kind of the thermodynamic cycles of various things. So this is a traditional vapor compression cycle. This is the compression in the compressor, the condenser, condensation in the outdoor condenser, expansion through the expansion valve, and then the boiling of the refrigerant in the evaporator. So when you're using the outdoor air, you have to compress it up to this pressure so that you can condense it at that temperature. When you use water, you're pressurizing it to a much lower pressure because the water's at a much lower temperature. This has a double benefit. It requires less power, and you get more cooling. So it's kind of a double whammy of good things that happen when you have a lower condensation temperature. So there's 3 modes of operation: the normal air-cooled mode, the discharge mode, and the recharge mode. The discharge mode is on peak from 3 to 7 p.m., and then the recharge is starting at midnight until the system's done cooling back down to its original temperature. And then the normal operation is all the time in between those two things. So I'm assuming in my model that the temperature in the evaporator is the same regardless of if you're using the water-cooled condenser or the air-cooled one. And I'm using a tank temperature range of 60 degrees Fahrenheit to 75 degrees Fahrenheit, in case you were wondering. So modeling of the system, the way I did this was I used the ECAT audit data and weather data, and I used this program called BOPT, and I built this. It stands for Building Energy Optimization. It does energy modeling of buildings. I use that to calculate the cooling load, like the thermal load that the house needs for cooling, and then I put that into a MATLAB program where I use some compressor models and other things to calculate, based on the water volume and tank temperature limits, and discharge, recharge times, what the power demand is and the total energy consumption from the compressor. And then that's how I use that for both an air-cooled only case where there's no thermal storage and a case where you have various volumes of thermal storage available. So for simplicity, I'm assuming that the water is maintained at a constant volume, that you're not losing water during the thermal storage operation. This was primarily because I'm focusing on whether or not the thermal storage benefits were there to begin with, because if they weren't, then this doesn't really make sense. So kind of idealized, the water level staying the same. Does this make sense for thermal storage? So kind of how this would work in real life is if you had city water to refill it up and that you're having negligible evaporation losses during the day. And those are both very reasonable to assume. Like I said, the goal is primarily to determine the feasibility of the thermal storage. So this is a plot. I ran the model using 5 different compressor models over a range of 1,000 to 5,000 gallons. for 2 weather periods. 2011, which was our hottest summer on record here in Texas, so that's kind of a best case scenario in terms of the thermal storage performance, and then also using typical meteorological year data, which is kind of more of a mild scenario. And what this shows is that this line represents the average of the 5 compressors. And there's a slight increase in performance as the volume of the thermal storage gets larger, but the biggest spread is between individual compressors. But the order of magnitude is all roughly the same. So on average, this is about a 40 to 44% peak load reduction at an energy penalty of between, this is 8.1 on average and 6.5% on average. This is for 2011. When you run it with typical meteorological year data, where I think the highest temperature for the year that they use is 99 degrees or something like that, it's kind of what I would consider a mild summer. The peak load reduction drops by about 3 to 4 percentage points. This is about 37 up to about 40.5. But the energy consumption increases significantly also by about 3 or 4 percentage points. So the performance of the system is impacted by both weather, compressor, and tank size, but the biggest factor is compressor. So compressors operate differently. They have different styles of compressors. What this suggests is that you need to pay attention if you were going to design a system around this, that you find a compressor that operates very efficiently at low delta T or low condensing to evaporating temperature differential, those low pressures. Weather also has an impact. It operates best on very hot afternoons and those days where there are very large day-night temperature swings, because the air-cooled condenser operates least efficiently at very high temperatures, and so if you have a mild day, it's not operating that much less efficiently than the water temperature that you're using. And then lastly, the tank size. It is an improvement as you increase in tank size, and this is based on just the same thermodynamics. That's why all of the compressors had roughly the same trend. But this model is also assuming a well-mixed tank. The results of it change if the tank were to be stratified, meaning if you're not assuming that the tank is at one temperature and that there's a temperature gradient, like a lower temperature on the bottom and a higher temperature on top, then you might see more of a definite cutoff in terms of performance benefits for going to a larger tank. So conclusions and future work. Conclusions, the peak load reduction over both of those time periods and all of the compressors was between 28 and 53%. The energy penalty ranged from about 5% on the lowest end to 15% on the high end. The performance depends heavily on several factors, primarily the compressor and its efficiency, but also on outdoor temperature and tank size. Future work, the goal of all this research and what it's leading into is I want to do an integrated model for economic assessment and optimization. So first I'm going to take this thermal model and integrate in water collection and consumption. So looking at how water draws for irrigation, how water inputs from rainfall and also from the gray water production from the house, how that might play into how you operate the system, the temperatures of the water in the tank, etc. I want to then take all that information and incorporate capital and operational costs, and as well as utility rates for the local area, kind of build an economic calculator with that information, and then optimize for tank volume over various scenarios, such as best value given the current market conditions, which might be none of either, best value given potential market conditions, so like maybe a high electricity price, kind of capacity constrained market, or a water scarce market where you might have very high water utility rates. And then also looking at lowest cost system to meet certain performance criteria. So if you want to say I want to be entirely rainwater for irrigation, that's my goal. What is the lowest cost system or lowest size system to meet that goal? That is about it. I would like to thank my advisor, Michael Weber, my research colleague, Josh Rhodes, for their help on this research. My sponsors, UT Austin, Pecan Street, and Department of Energy. Are there any questions?
Thank you. We're going to hold the questions for both of you till the end. Thank you, Charlie. And we'll just switch that over. And Erik is going to talk on commercial innovations in community-scale distributed generation. This should come on here. There we go. Yeah. Looks good. There you go. All right.
Awesome. All right. So I'm actually going to talk about something much different. So what I want to speak to you about tonight is some research that our research group, the Energy Systems Transformation Group, has been working on and had in development for a couple of years. Earlier this year, the prior study in this series went to press on the value of solar, which is an emerging model. What I'm going to talk to you about tonight is commercial innovations, primarily focusing on community scale distributed generation. So the first thing I want to do is do a really high-level overview of kind of where we're at. What's the state of play here in the distributed generation space? So I want to talk about the U.S. market, some context factors, what's sort of the nuance relevant to this topic for utilities. And then I'm going to get into sort of what shared renewables look like right now in this sort of early stage of their deployment. And then the study that we've done, sort of triangulating some of the insights that are available at this point. So this is the high level. So this is like where we're at the very high level. So this top left side, you see, this is using California as an example. This is the basic way we think about distributed generation. We have a federal investment tax credit that's been around for a while. It was extended through 2016 through the stimulus package. That brings down the PV net price. The CSI is just the contribution of California's portion. So the net price is subsidized to an extent by federal and state incentives. The other side of that, which I'll talk about a little bit more in a slide in a minute, is the RPS standards. So there's a combination of carrots and sticks that play in different states. The next one over here, that's just showing, what you all know, module prices are coming down. So since 2000, there's been a huge price. The line you see is the levelized price coming down across utility, residential, and commercial distributed generation. This sort of breakdown on the bottom, I just threw this up here to show you, this is comparing the way that we have it right now versus Germany, to show you that, the installed labor, customer acquisition costs, and then the profit and overhead. Those are sort of places where there's a big delta between what the installed cost here versus one of the other countries that's being very aggressive in distributed generation. So that's just the high level. Again, this is sort of showing you the same thing on the left-hand side, just showing that we're moving and things just in the last couple of years, it continues to have this high uptake rate. But this is actually where this sort of study around community scale stuff comes, the contradiction is kind of illustrated here. This is the way that we think about it right now. We have residential distributed generation, non-residential distributed generation, and then we have utility scale. That's sort of the universe of solar right now. But if you look over at the other one, what you see, you have this little black dot, and that is what we've deployed to date. The yellow circle around that is basically what the potential for this approach of deployment is. However, the orange and the blue circles here, what that represents are the households that don't have access to this type of deployment, not because of the cost of systems, but because they're either residents of multifamily homes, or they maybe they are a residential unit, but they don't have proper insulation, or just a poorly sited rooftop. So it's not a good fit for solar, doesn't make sense there. So that's really, as these prices come down, new consumers come into play, but so does it become more important that we start to address what the fit of our strategy is. So this just adds another layer, looking at the state of play in terms of context. So, this map shows you all the RPSs. You can't make much out of what they specifically are, but they range, quite a broad spectrum of stringency. So in California, it's going to be, it's 33% by 2020. Texas, we satisfied ours a number of years ago, So it plays much differently, and then that overlaps with the value of the generation capacity when it's done in geographic locations that have better solar resource. So if you're in Arizona, the value of the incentives is higher than if you're in New Jersey. New Jersey also and Massachusetts are also very aggressive with distributed generation. Now, utilities. So when you heard Paul Hodges talk about this a little bit a couple of weeks ago, the thing with getting into the market with renewable energy is that you only have a number of consumers, and that is the utility system. So these two kind of pie charts. The first one shows you throughout the U.S. currently, most customers are served by investor-owned utilities. What the other chart is showing you is that most utilities are actually publicly owned utilities. So there's not very many IOUs, but they serve the most customers. That means they're huge. So they're a big player, but so are publicly owned utilities and electric cooperatives. I broke this out a little bit by some of the states that are important in this to this topic, just to show, California, the three primary IOUs there, San Diego Gas and Electric, Pacific Gas and Electric, and Southern California Edison. They serve, most people there. And then Texas, we have a kind of a distribution of all three. So it's that's varying across the state, and that's important to the fit of distributed generation and what's going to work best. So that was sort of the overview of the state of play. Now, I want to kind of introduce this topic of community renewables, explain the two sort of models that exist, then we'll get into the study. So community solar is kind of exactly what it sounds like. So it's when two or more people in the same area come together to invest mutually and mutually take out the benefit. Typically, this is in situations where they are poorly sited and they use an off-site location. So they'll use a centralized location, benefit from economies of scale, benefit from optimized siting, and a few things like that. Utility-sponsored community solar is pretty easy to understand. So you basically, if I'm a utility, I build a solar installation, and then subscribers perhaps buy it on a voluntary basis. They get the value back to them on their bill through virtual net metering, which basically just takes off the proportion that they've bought with their share of the shared system. And then the utility and everything else is essentially the same for the utility. It's just where the customer is paying for their power. Now, special purpose entities are a little bit different. These can be either private sector companies kind of leading the way or groups of individuals leading the way. What happens there is they capitalize on the incentives, sell back through net metering the power to the utility, and then they give a virtual credit to the customer for the amount of the system that they owe. So they basically pass back a portion of the credit and the generation value to the customer. Now, something I want to point out here to keep in mind is that this is sort of the thing that's important to utilities, is that the relationship between the consumer is very different here. So on the first one, with utility solar, the customer is still getting satisfying all of their demand, whether it's through the balance beyond their community solar investment or the community solar investment is all still going through the utility. Here, it's not. Here, you still have the problem of the customer primarily coming outside of the demand service of the utility. So we thought this was interesting, so we did a study. Now, this is really new. So before 2008, there were 3 community solar installations that are all very beta. Now there's upwards of 65. We have data on 61 of them. That's all happened since 2008. So what do we do in that situation? We have limited data. So what we do is we triangulate. So the first thing I'm going to do is share some expert elicitation insights that we got from surveying and interviewing utility leaders around the country. So these are renewable energy and distributed generation program managers. And then I'm going to give you some insights from an empirical review we did of the systems that we have data on that have already been deployed, both special purpose entities and utility scale and utility sponsored. And then I'm going to show you one empirical inquiry we did into the relationship between encroachment of residential PV on adoption of community solar from the utility standpoint. So yeah, so this is a mixed methods approach. I'm going to look at some survey responses, then also some data, and then look into maybe a slightly more sophisticated use of the data a little bit farther on. The interviews, we interviewed 7 and then got survey responses from 26 utility leaders from 12 states. We had a pretty good distribution of the different ownership types, which would be the the municipal, investor-owned, and the cooperative utilities. Then the deployment database, which is the one looking at the recent projects, we have 61 projects, 58 of those since 2008. If you look at the inner donut here is the frequency and the outer donut is the installed capacity. I just put that up there so you could see sort of the difference. One of the morals of the story will be that munis are putting out a lot of the capacity that's coming through community solar. You also want to note that Colorado and Washington are the only ones where we will have both community on the special purpose entities and the utility sponsored community solar. And then finally, I'm going to take you through a little inquiry we did here, looking at 12 utilities that we had community solar projects, and also had PV data, so we knew what the residential deployment of PV was for the territory between 2000 and 2012. And then we took a sample of non-community solar endorsing utilities that were similar in terms of the number of customers served and the RPS stringency within the state. So going back to the surveys that we did, we're basically asking this one overarching question, which is, on paper, community solar has a big benefit to utilities, but what do we know? How does what we know match up with what they perceive in the way that they look at programs and distributed generation? So there's all these potential benefits. So our prior work, done by Griselda Blackburn, Claire McGee, and Varun Rai, looked at value of solar more generally, found that solar is really only seen as incurring savings, just really in terms of generation capacity. You hear a lot about the savings to a utility from reduced transmission and distribution and line loss, and they're not, the responses we got there was that they're not seeing it. Even if it shows up on paper, no matter how you look at it, they're not seeing it. So when they make decisions, their decisions are what matters here. So we took that into account when we looked at this. So with the survey and interviews we did here, what was important in terms of thinking about community solar from the utility perspective? Well, customer demand. That was a big thing. It was a little bit surprising. They're very in tune with what the customers want. And there's a potential reason why that's important for community solar that we'll talk about in a moment. Another thing would be impact on revenue. So that's a big consideration. How does adoption keep revenue in or out of their service territory? And then and just in solar programs generally, what's important? Well, contribution towards RPS, that's a big deal for them. Again, customer demand turned up again. And then the generation mix. So it's nice to see that that's sort of in their decision-making process, they are valuing including more diverse technologies under their portfolio. At the tail end of this, we asked a lot of questions. There's details in the actual paper that's coming out, but some of the meta takeaways here is that utilities are really genuinely concerned about the erosion of their revenue from distributed generation. Right? When customers do traditional distributed generation, they take their demand out of the utilities, out of the utility service, and they just satisfy around the margins. That's something that they are concerned about. Also, something that's resonated again and again was that, regardless of what it looks like, the avoided costs and the potential savings just are not looked at as a one-to-one relationship when it's a utility decision-making process. They're not looking at it that way at this point. Then a third sort of meta takeaway here is that, these programs aren't that nimble. So if they're Austin Energy and you're going to develop a solar tariff, you can't change it in May and then again in August and again in December and have any kind of outcomes. So you have to make decisions with imperfect information. So they're sticky. So that's where we left off with the solar survey, and that gave us some insights for how to look at this, what happened recently in deployment. What you're seeing here on the top, you have the installed capacity. So since 2007, a lot of the installed capacity is really coming from Colorado and from Arizona. Even with everything that you see down here, which is the frequency for all these states, Arizona and Colorado make up some of it, but not nearly what you see up there. So that's just kind of illustrating the distance between the frequency and the installation capacity. Over here on this side, what you're seeing is, again, the same thing reflected, that a lot more of the capacity is coming from the utility-sponsored and a lot less from the special purpose entities. But the special purpose entities, the frequency is increasing more. And if you see down here, I threw this one in down at the bottom just to illustrate that special purpose entities are making up more share. It's not being muted completely by having so much more come out in terms of capacity from the utility-sponsored community solar. Let's see, did this come out clearly? Okay, it didn't come out too bad. So there's just a couple of key takeaways that you can see here. I'd like to point out, first of all, that if you look into investor-owned utilities here, there's essentially very, very little of the community solar happening in the U.S. right now. In investor-owned utilities is happening as utility-sponsored. There's only 4 systems that we found. The exact opposite is true with municipal utilities. Almost everything is happening at municipal utilities under the utility-sponsored approach, and then it's sort of middling in the cooperatives. The joint billing, joint ownership, and virtual net metering, those are just different models for how you might do special purpose entities. So that's sort of where we leave off with those insights from the recent deployment. So now we get to this question: what do we know about how utilities are looking at the real or perceived threat of encroachment of their revenue by PV. So we have a data set from Lawrence Berkeley National Lab. We took that data, we looked at the deployment over 12 years, and then what we did for every utility in that sample I described earlier, we took the 11-year cumulative total, and then we created what's called a sensor variable, which just means this is the year where we met some threshold. In this case, the threshold was the year in which that utility hit 3% of the eventual 2012 cumulative total. So 3% of what would be the eventual total. And what that's supposed to represent is the time at which they hit that threshold should reflect whether or not they were seeing a lot of penetration early on or later on. And that's important because we have if you look back to here, this time period between 2008 and 2011, if they were making decisions to put in community solar, they were looking at a formative period between 2008 and 2011. So that's when PV matters for that uptick that you saw there. So, so we're looking at this 3% variable. And on the left-hand side, what you see here, this is sort of the crude look. So what all these are being compared against are REX communities and IOUs in the non-community solar group that we sampled. And they're essentially many fewer of them in that formative period between 2006 and 2009, seeing a lot of utilities hit that 3% mark. So that's one way of looking at it, but we wanted to get a little closer in. So what we used was a process called Kaplan-Meier failure estimation, and this is something that is very insightful in the way that we're looking at this. If you look at the top two, you have IOUs and rural cooperatives. The IOUs and rural cooperatives, what you have on the x-axis here, this is essentially the propensity for any utility in that group to hit that 3% mark. They're more likely as you go up that x-axis. So, the y-axis. So for the community solar group, municipal utilities and cooperatives were much more likely to hit 3% earlier on. That's what the distance between those two lines are showing you. Interestingly, you're not seeing the same thing. In fact, they track almost exactly for the IOUs. And that's, we have a possible explanation. But the takeaway here is that, yes, for IOUs and for RECs, it does look like they would have been signaled that PV encroachment was happening a lot faster than their peer group that did not end up adopting community solar. So, but let's think about that IOU question for one moment. There's sort of an explanation in here that you can get into earlier, which is that IOUs don't have the same flexibility in terms of the way that they use investment tax credits, and they don't have the same flexibility in terms of how they distribute the benefits of incentives. So what that means is that if I'm an IOU and I want to deploy community solar, then the cost of that investment has to be passed through to the customer through the price of the electricity. And if you're in a liberal market like Texas, what happens? Well, your rate in relation to your competitors goes up. So you have to, instead of a municipal utility or a REC, where what they're looking at is your current cost versus your future cost, here they're looking at their current competitive price much more firmly than their in relation to their competition. So they have much less flexibility both on using investments. They face more transaction costs, but especially in how to amortize the investment in a way that doesn't actually put them at a competitive disadvantage. So the good way to summarize that is to say, are you more worried about this potential nebulous threat from PV encroachment or the known immediate threat from increasing your rate in relation to your competitors? So that's our explanation for why IOUs are sort of following a different path there. So this has been a really exciting study. There's a lot more to it, especially on the policy side. A couple of things I'll put on your radar just briefly as I wrap up is that California has recently decided to do 600 megawatts of community solar in the next handful of years. It's going to happen very quickly. They're doing it through the Public Utility Commission. That's coming from the hope to imbue more equity in the distributed generation programs. They see the cross-subsidization as being a big problem there. And then just generally, there's been a lot of regulatory pressure towards not cross-subsidizing, and that becomes more important as you get a lot more distributed generation. So big thanks to Griselda Blackburn and Claire McGee for providing the antecedents of this research before they left to go on to be the vice presidents of companies and be big, important policy advisors in DC. CG Dong for helping us with the data from LBNL, and also Trevor. Trevor was helpful in helping us getting this ready by helping take some stuff off my plate. And it's always good to have a guy like Trevor, and he's in sometimes a thinkless position. So I'm taking this moment to do the thinking part to him, and then also to Varun Rai. And I'll leave it there.
Well, thank you both very much. I want to open it up to questions now. I'll go around and pass the mic around. Do you have your... So questions for either of our speakers?
My question is for Charlie. You were talking about inputting rainfall into the model for like tank level variations, etc., right?
Yeah, in terms of incorporating rainfall in terms of tank level and collection, all that,
So
yes.
the system that you've designed is meant to be run only in the summer or throughout the year?
Yeah, it's meant to be operated for thermal storage purposes, definitely in the summer. The idea is that for a house, if you were going to size it, if you needed if you were going to put in like 5 or 6 or 7 or 8,000 gallons, maybe you only need 2,000 gallons worth of water for thermal storage, and you have the rest of that capacity for rainwater that can fluctuate. Another thing is something that I've heard some people from Austin Water talk about is having people with rainwater systems in the summer, since they are typically dry, have them fill them up off peak. They're kind of like, they have like peak times where their pumps are all running, people are consuming water. for irrigation, they could, people with rainwater systems could fill it up off-peak and then irrigate with that water later in the week. So you get some benefit from reducing water consumption kind of early summer, spring, fall. Maybe in the dead of summer you're on city water, but kind of like overall your annual water consumption could be significantly lower.
Actually, my question was like, is rainfall that frequent in Austin that it makes a significant difference in your model? Like,
in terms of total collection for the year, or in terms of frequency and in terms of changing the level?
in terms of, I don't know, the model is supposed to do daily fluctuation in water level, right? Isn't that what you're doing?
Yeah, so that would be more, it rains kind of on average every several weeks, month. It depends on the year, obviously. It is a little bit punctuated where we do get, like yesterday, we had 29 hours of rain straight. It set a record, I think. But then there were spans where we hadn't had rain for over a month before that. So it's kind of more just kind of the granular. It also matters more for the gray water system where people are consuming water in the house every day. It's more of that accumulation of water from day to day.
And is there a pilot planned?
I am working on it.
Questions?
Thank you both for excellent presentations. Good to see you again. Thanks for traveling all this way to come visit with us. Question for Charlie. What about some special consideration? I don't know, you've got plenty of work with the modeling, and that makes sense. Just wondering if there's any additional work on filtering the water and making sure it doesn't have acidic properties versus, I guess, a typical glycol-based closed-loop system that people think about. And then I've got a question for you.
Yeah, so I have two versions of this system. This one is the condenser side indirect system. I didn't show the schematic of the system, but yeah, there would be some level of filtration and treatment just so you're not fouling the heat exchanger significantly. In this type of system, if you are using it for irrigation on a weekly basis, you're turning it over using the water relatively frequently, but you would treat it up to a certain extent. I am working on another design that is using a hydronic air conditioning kind of system where the thermal storage would be inside the chilled water loop, but in an indirect manner similar to that one. Again, you're isolating the water from the hydronic loop, so you're not mixing it directly, but in that one it would also be treated as well.
Okay. And Eric, interesting. What about the different, can you describe maybe the different business models or business structures required for the community scale solar? Because I think from what I've heard, munis still have to have a private entity create the community level storage so they can get the investment tax credit, for example, because they can't. So I understand that. For IOUs and co-ops, do they have different flexibility? How would you structure that? Do they perceive community level storage as good of an opportunity as utility scale in preempting the hollowing out syndrome, or is it not quite as attractive? Or
Yeah, I think that, so let's take your second question first. The utility scale, they are, distributed generation is completely on a different set of decisions. Even a lot of times you look at a utility and they actually have, different teams and departments looking at those two things. They're not done in tandem. So I don't know if they're looking at, utility scale. That's going to be a completely different beast. I would say that, and it's essentially like you said, you do a PPA with utility scale, and you just, it has to meet their price expectations the same as everything else, and maybe you can benefit from the variability. But in terms of the different business models, yeah. So what he was alluding to in terms of the investment tax credit is that municipal utilities, publicly owned utilities, don't have a tax appetite, and the reason for that is because they finance these projects through tax-free bonds. So to them, they don't have a tax appetite on the project because they didn't invest any taxed income. So they can double dip though, and they can have a third party. There's some transaction cost to that, and that's for both. No matter what you do when you involve a third party but they can get some value of that. So that's where that happens. However, a number of these projects on the utility-sponsored community solar are typically done directly from the utility. They own it, they run it, a lot of the largest ones, so it's not being hosted through the third party. However, you don't know, there's going to be a huge deployment, path taken that'll be different than what's already happened. But yeah, in terms of utility sponsored, right now I think the focus is on keeping it on their side of the ledger. That's kind of what you're seeing.
Hi, Eric. I have a question about so the utilities that are implementing community solar. Is there also a trend within those to change their rate structures in terms of decoupling, or just are those coupled? Is there any indication that once they've adopted community solar that creates some incentive to change their rate structure?
Yeah, so we have some discussion on that in the paper that's coming out. But it's actually, you can't track it actually. There's a lot of movement right now, and if you look at what's going on with distributed generation, because of the problems with cross-subsidization, because of the problems with basically having to cap the amount of deployment you make available with your tariff or with whatever solar credit you use across the all the options available. There's a lot of pushback both from utilities not wanting to kind of arbitrarily cap, and then also so they're wanting to scale back from that side of it, and then also the cross-subsidization thing has become very poignant. In fact, they're losing, sometimes there's loss of rate cases, things like that, at PUC commissions because of the inequities from cross-subsidization of distributed generation. So those things I don't think are I think that the marginal impact of having adopted just is collinear to a number of other bigger, broader things. Just distributed generation is typically, even for the large ones, larger programs across the U.S., they're typically smaller in terms of the things that force that particular question.
Anyone?
So I got a question for Eric. Why would a utility, either a muni or a investor-owned utility, invest in community solar rather than a third-party residential solar company? Because I feel like residential solar companies are taking more of the high-paying customers away than community solar. Because I feel like more residential solar is a little more prevalent now than community solar, so are utilities kind of weighing both options in terms of investing in community solar as well as third-party residential solar companies?
So the residential solar, residential distributed generation is sort of what I'm talking about when we're talking about hollowing out the residential service, customer service area. That's actually what's contributing to the problem. So the cross-subsidization, that's who gets those incentives, are people in that model. So that's how we're doing this right now. If you're getting a rooftop solar, unless you're in a place where there's no incentives, you're getting it through a residential installer. And then there's commercial, and then there's utility scale. But what you're talking about is the way that they're doing it now. And community solar could either, we're arguing, essentially what I'm arguing tonight is that it's an ameliorative effort. It allows utilities an option to keep the customer base so that they don't end up having to come up with extraordinary end runs to recapture what's lost when a customer goes solar, to make it basically unbounded so that they can endorse solar, and if solar ended up somehow taking over 100% of it, they would still be a viable option. That's not the way it's done right now, because the incentives are so expensive and cross-subsidization. When I was at South by Southwest Eco, and there was a panel, and the guy from NRG which is a large, electricity provider, was talking to the guy from National Grid, which is the largest one in the Northeast, and the guy from National Grid had just said, described their distributed generation, and the guy from NRG interrupted and said, I love that approach. I'm going to move up there because it sounds like if I move there and get solar, he's going to have all my neighbors pay for it, and that's essentially, that's what they're getting away from, because it doesn't hold up as you start to scale up, and that's where we're at now. We're at that inflection point where we're going to a lot of deployment.
I actually have a question for both of you. Charlie, I'll ask you first. I'm just curious if you've heard the recent efforts to do a bit of what you're working on here, but with deep ocean water, bringing really cold water from the ocean floor, and if so, what kind of price differential you have, because you talked about scalability and the fact that small scale it doesn't, I would guess the same given the pumping of water is costly. I'm not sure if you have any comments on that.
Yeah, so I guess you're referring to kind of like, so I did my master's on ocean thermal energy conversion. I know there's a similar thing that is used where you're pumping that deep cold water for air conditioning in buildings, typically done for buildings on the coast, large hotels, that sort of thing, or that's what's been proposed for. This is meant to address, like typical Austin house, so you wouldn't be able to pump that water hundreds of miles and keep it cool. It's meant to be kind of, sort of the distributed level way to make this technology that's currently only at the very large scale, at the kind of campus level, large commercial type scale, make it available to residential homeowners, since that's where the biggest kind of load is that's currently unmet. Trying to address really that kind of untapped potential for residential air conditioning load shifting. Now, something else that somebody might ask about is the kind of demand response programs with thermostats. This kind of performance is a little bit better than those systems. Those are typically 10 to 25 or so percent, but that's typically over a 30-minute time span where they're cycling it off, and they have to cycle off. They can't cycle off every house for 4 hours. It's one house at a time for 30 minutes, and so it's kind of on aggregate not as big of a reduction per house. So this is a way to significantly reduce the load from lots of houses for a long period of time.
And just really quick, what scale are we talking about when you say campus-wide? If it were homes, how many?
So I think they typically start on the order of, I want to say, several hundred, like 100,000 gallon type system, multiple 100,000 gallons, kind of like the minimum size. And the way that it is also, it's only really commercial because of the way the rate structures are done. There's a demand charge at the commercial level that's not at the residential level currently. So there's kind of added benefit to shift or reduce your demand at the commercial level. Same with time of use pricing, there's that as well that kind of makes it, the rate structures are there for commercial thermal storage but not for residential. And so this is kind of trying to start the conversation of, well, maybe if there were a system that were there that could kind of do this sort of thing, rates could then be developed for it. It's kind of a chicken and egg sort of thing.
That's very interesting. Eric, I wanted to ask you just a little bit more about the data set you talked about. Did you see any fluctuation year to year, or was it a fairly continuous? I'm just thinking about the deregulation, for example, of markets that happened in that same time period. Did that have any effect on the data?
You mean, are you talking about, let's see the chart.
Yeah, there's a really interesting graph, which I'm still grappling with.
Here?
Yeah. So you start in 2007, right? And when did Texas deregulate?
Texas is not in this data set.
No, sorry, go back. It was one before that. Or two.
Wait, are you talking about?
There we go. This was way before.
Here?
Yeah, okay, here we go.
This is 2000. This is 2012.
Okay.
Yeah, so this is the distribution this is how the customers served, and this is the actual number of utilities. So more utilities, more co-ops, a handful of IOUs, some communities. But yeah, the Texas doesn't factor into the community solar thing. We don't have any community solar. There are community solar programs though on the advent in a number of cities across Texas that will be coming out starting next year. So you should be on the lookout, including City of Austin just announced that Austin Energy will do its pilot program in community solar next year. So we'll be getting it here at home. There's a question right here.
Hi, question for Eric. The grid is, as it is built right now, it's designed for like large generation from to supply everyone. I think community solar is very promising, but how would the grid be impacted, and would some things need to be updated if it was widely adopted?
So that's a good question. That, though, depends on how you look at it, because there's not going to be, the grid implications are the same, possibly slightly more ameliorative from community solar than from residential solar, just because utilities may be able to incentivize better system siting and a couple things like that. It's vary around the edges. Otherwise, I don't think community solar is going to be, and according to the data that we have from utility program managers, they don't imagine that it's going to be very different from residential solar. And there's some known pains to residential distributed generation around, particularly around the uncaptured costs of those T&D charges, line loss, all that stuff. In Griselda Blackburn's paper, the one that preceded this one, they showed 50% of utilities capture more than 50%, or the majority of utilities capture more than 50% of all those charges, the T&D, the line loss, all that stuff through volumetric charges, which means that distributed generation fails to capture the costs that they incur from the two-way flow of power back and forth. So yes, there definitely is degradative impacts of distributed generation. So I think, but those problems I think are the same, and there's just maybe a slight benefit on those, and not that particular question. There's not a lot of difference. The real value comes from the other things having to do with the preservation of the utility business model and better customer and a much bigger customer segment. There's so many consumers that are not eligible for traditional residential solar that would be eligible, including some of the high-income people that haven't been eligible up to now.
Well, I want to thank both of our speakers, Charlie Upshaw and Erik Funkhouser, very much for presenting today. And thank you all for coming.
Fun, man. Yeah. See you around.